Hi guys, welcome back to the channel. This is a 20 teeth gear and this is a 40 teeth gear. If I turn the large gear using the smaller one, the large gear will have half the speed of the small gear, but it will end up with twice the amount of torque. Torque, however, is not the only thing gained by the larger gear. The large gear will also end up with twice the resolution of the smaller gear. So if this gear happens to be a rotary encoder with say a resolution of 20 steps at 18 degrees per step, then the large gear will have a resolution of 40 at 9 degrees per step. So double the resolution of the small gear. This is a very simple but extremely useful mechanical concept. And in this video, I'm going to be using this concept to make a pretty accurate magnetic encoder servo. This is the rotary encoder I'm going to be using in this video. It's based on the same magnetic rotary encoding method featured in many of my projects. I already made a few videos explaining how it works, so I won't go into too much details about it here. Anyways, this encoder has a resolution of 60 steps, which is 5 degrees per step, but we're going to be gearing it up to achieve a much higher resolution. And although this encoder was originally designed for user inputs, I should be able to easily adapt it for a gear train by replacing the knob with a gear. So this is the design I came up with. It's a compound gear system with 4 stages. The first mate is between the motor and the magnetic rotary encoder, which is placed here. And if I zoom in a bit, you can see the magnets installed on the gear. So we don't actually care about this first stage. The reduction between the motor and the encoder is just to help the motor turn a bit easier. The 3 stages after that are the stages we really care about. So if I do a partial explode, so on the first stage, which is the yellow gears, we have a 20 teeth gear mating with a 54 teeth gear, which results in a gear ratio of 1 to 4.5. And then on the second gear, we have a 14 teeth gear mating with a 64 teeth gear, which results in a gear ratio of 1 to 4.57. And then finally, the output gear is a 46 teeth gear mating with a 12 teeth gear. Now, by the rule of compound gears, the resulting resolution at the output is a product of the 3 gear ratios before it. So in our case, starting from the rotary encoder, which has a resolution of 60 steps per revolution, so we multiply 60 by 4.5 and then multiply that by 4.57 for the second stage, and then multiply that by 3.83 for the third stage. So the gear ratio from the encoder to the output gear is 1 to 78.857. So what we've essentially done is taken the 5 degree step resolution of the encoder and then multiplied it by 78.857, which now results in an output resolution of 0.076 per step. Now you'll notice I also used herringbone gears starting from the magnetic rotary encoder. That's because herringbone gears tend to self-center themselves. So that should help align things in a compound gear system like this. So that's it for the design. Let's get to actually building the gearbox. While my printers were printing, I proceeded to cutting the required shafts from a 6mm steel rod I had lying around. I cut out two lengths of 43mm for the gear shaft and a long 100mm for the output shaft. I marked out a little 10mm section on the output shaft and I cut a slot into it. This will help when attaching the shaft to the output gear. I printed all the parts in PLA except for the bearings, which I printed in ABS. To assemble the gearbox, I am using self-tapping screws. Whenever I use self-tapping screws with 3D prints, I always apply grease to the holes. It helps the screws going smoothly and it also minimizes stripping whenever I need to take them out. I can highly recommend doing this. It just ends up being a bit messy. After attaching the standoffs to the base, the encoder is supposed to go in early on, so I will assemble it next. But before that though, a quick ad from this video sponsor, GLC PCB. In addition to manufacturing and assembling your PCBs, GLC PCB now offer 3D printing services in a variety of engineering materials, as well as a new global parts sourcing service. It used to be that you were limited to only the parts available on GLC PCB, but now you can source components from major suppliers around the world, saving a fortune on shipping, especially if you live in a place where component sourcing can be a headache. So check out GLC PCB using the link in the description and you can get a discount on your first PCB order. Huge thanks to GLC PCB for sponsoring this video. Now back to the assembly. After assembling the encoder, I realized I forgot to solder the header for connecting the encoder to the board, so I had to take it apart to add the header, and here you can see where the grease helps. With the encoder reassembled, I can now attach it to the base by simply aligning the holes and securing it. with 3 M2 screws. The motor then goes on after. The next step is installing the gears, but first I have to glue on the secondary gear to the gear that goes on the encoder. Because of the tiny holes for the encoding magnets, I could not print these gears in one piece, so I have to glue them together separately. This is a herringbone gear, so orientation matters. Thankfully, I thought to add a little hole to the part so I can easily identify which side is up. To glue the gears together, I used one of the shafts to align the gears. Probably not the best way to do this, but it worked out just fine. The gear shafts went on next with some persuasion. You'll see here one of the disadvantages of using herringbone gears. They don't mesh together vertically, so I had to kind of arrange them in the hair before fitting them onto their shafts. A bit awkward, but not impossible. For the output gear, instead of screwing directly into plastic, I attached a heat insert first so I can screw onto the shaft through the insert. This is the better way of attaching a 3D printed gear to a shaft in my opinion. Before the output gear is attached, I installed a custom 636 bearing followed by a spacer. The gear then goes on first, followed by the output shaft. To secure the shaft, I simply align the slot I cut into it earlier with the insert hole on the gear. And then hold it in place with a screw. The last gear goes on the motor and that's just a press fit. The only part left to install is the top cover. Not really in my case though. I still have to attach the magnets to the gear on the encoder, so I wasn't sure if I was going to have to reprint the gears or not. So I deferred attaching the magnets until I was sure everything fits as they should. The gears seemed to move well enough, so I took apart the gears and installed the magnets in the familiar alternating pole configuration. I repeated the gear arrangement, screwed on the top cover, and that's the magnetic encoder servo assembled. Unfortunately, during my initial test, the motor released the magic smoke and now it can barely move the gears. Not a big deal though, I just went to a scrapyard and got a few more random motors, out of which I found one that seems perfect for the gearbox. After swapping the motors, I connected it to a H-bridge driver module controlled by an Arduino just to test, and it worked great. A bit noisy though, but I think that's to be expected in a gear train like this. Now, to control and test the servo, I'm going to be using a Raspberry Pi Pico board, and I'll be writing all the code in C++ in Visual Studio Code. I'll explain the main functions in the code later, but first, let me explain how things are connected. Despite the mess of wires, the connections are actually pretty straightforward. So I have two magnetic rotary encoders here. So this is one magnetic rotary encoder and the second magnetic rotary encoder, which is built into the servo. Both encoders are connected to the Raspberry Pi Pico. And if you go to the GitHub repository for the magnetic rotary encoder, you'll find details on how to make these connections. So I have two rotary encoders connected to the Pi Pico. The DC motor is controlled by this H-bridge driver, and I have a separate 12 volt line coming in to supply the driver, which in turn supplies the DC motor. Now, the actual control signal for the motor direction comes from the Pi Pico as well. So the Pi Pico controls the H-bridge via two PWM signals, which controls the direction of the DC motor. This magnetic rotary encoder will be synchronized with the magnetic rotary encoder in the servo, so I can control it using this external encoder. So we can see exactly how geared up this servo is, because one full revolution of this encoder will only result in about 0.08 degree movement on this output gear. So that's basically it for the connection. I also attached this little pointer so we can easily see the movement as the gear rotates. Before I turn this on and show you exactly how this works, let me quickly explain the important functions in the code. So this is the code I've put together for controlling the servo. This code is based on the Pi Pico C and C++ SDK. I could also do this in MicroPython, but I found that MicroPython on the Pi Pico is significantly slower than the C and C++ SDK. So I generally prefer to use the SDK to program the Pi Pico. But you can check out the GitHub repository for the magnetic rotary encoder for how to use the encoder with MicroPython. Right, so the first section of the code defines the encoder mode used for the servo. Now, I've been working with the magnetic rotary encoder for years, so I've developed quite a number of modes based on the different projects that have featured the magnetic rotary encoder, like the Armsville dial and the pick and place wheel project. Anyways, I've simply set the mode to mode 7, and that's base resolution, and I'm using digital pins only. You can again check the GitHub repository to understand the differences between all these modes. I've just set it to 7 because it's the best mode for this application. A few of the other modes will work, but 7 is just the best. So right after that, you see the pin assignment for the rotary encoder. So the digital pins from the rotary encoder is connected to these pins on the Pi Pico, and I have 2 of them. So one for the encoder in the servo itself, and then another set for the rotary encoder that's meant to control the servo. Now, if you like to replicate my exact setup, I'll have a detailed connection diagram in the description so you can replicate my exact connection, and then you don't have to worry about the code at all. But if you decide to change the pin assignments, this is where you would update it in the code. The other parameters defined here are not really essential to this project. They're just copied over from the default example code for the magnetic rotary encoder. So I'm just going to skip through that. So this is where I set up two PWM signals on the Pi Pico. So I've set two of the pins on the Pi Pico, which is pin 13 and pin 12 as PWM pins. And these pins will be used to control the motor direction. So you can see here, I'm setting up two PWM signals, one for the forward direction and one for the reverse direction. Then I have a few more functions just to turn on and off the PWM. This section here is where I create two magnetic rotary encoder objects. So one for the servo encoder and then one for the controlling encoder, which I've just named my knob. So scrolling down a bit more, I'll have this code on my GitHub repository so you can reference it properly if you feel like it. Okay, this is the PID section. This is where I've defined the parameters for the PID controller. Now, one thing I should mention is the PID controller I'm using, which is this bit of code in this pid.h file. I've copied it directly from Phil's lab. He did a very good job explaining how you would implement a PID controller in code. So I've just copied his controller into this pid.h file, and that's the PID controller used to control the servo. So these are the parameters I've set for the servo, and I arrived at this value by doing some quick tests on the servo. I've also defined some limits for the PID controller in terms of PWM max and min values. And then right below that, I've defined the resolution multiplier. So this is the value we calculated from the gear ratio in the compound gear setup in the servo. This function here that says get encoder steps from degree is the function used to convert a desired degree position on the servo to the equivalent steps that the rotary encoder needs to make to achieve that degree. So it's just two lines. So on the first line, I'm simply multiplying the resolution multiplier by the desired degree output. And then on the second step, I'm converting the resulting degree into encoder steps. And I simply do that by dividing the equivalent degree by the 5-degree step resolution of the encoder. And that's what 360 divided by encoder base resolution will give you. And I just simply return the encoder steps that would result in the desired degree position. I get to the main section of the code. Now I just have a few setup code here. I won't go through that. All these are setup codes for the magnetic rotary encoder. I won't go through that. You can refer to that on the GitHub repository. What I really want to show you is just the main function here that says PID move. So essentially, whenever I enter a new set point, so this section here will use the PID controller to move the servo to that set point. And this set point can be modified by sending a direct command to the Pi Pico through a terminal, or I can use the encoder to increment the value and the PID will respond to that change as well. So that's it for the code. If you are replicating my exact setup, you don't actually need to worry about this. I'll have a .uf2 file on my GitHub repository that you can just copy into the Pi Pico. And then provided you've connected things exactly the way I have in my setup, it should just work right away. But if you're building a similar setup and you're doing something a bit different with the connections, you can refer to this code in its entirety in my GitHub repository. Okay, so let's go back to the setup and see how all this actually works. So I have the setup powered now, and you can see the H bridge is on, and there's also a red LED from the encoder. First, I want to show you that this is indeed a closed loop PID controlled servo. So if I try to like move it, you can see it returns to the position where it was. So if I try to move it, you can see it will always return to its original position. So that's the PID control in action. The PID could use some more tuning. As you can see, it's oscillating a bit there. So if I move this encoder, you can see I can change the angle. And as you can see, I have to turn the rotary encoder by a fair bit to register any kind of significant change on the output, and that's the result of gearing up the magnetic rotary encoder. So you can see it takes quite a bit of turns to move the output. So the actual ratio is 78.857 to 1. So I have to turn this about 78 times before I can get a full revolution on this output gear, and that's all PID controlled, so it's pretty accurate. I mean, as accurate as a 3D printed gearbox can be. It's pretty responsive too. One thing I can also do is I can control the Raspberry Pi Pico directly from my computer. So I can send some specific commands to the Pi Pico and then use that to set the output shaft to specific angles. So if I open PuTTY and then connect to the Pi Pico, you can see I'm getting the information about the position of the servo, and I also get information about the encoder steps that correlate to whatever angle the servo is currently at. So I can just send a custom command, which is md equal to say 50 degree, and then the encoder moves to 50 degrees. So you can see it didn't quite get to 50 degrees exactly, but that's 49.91, which is pretty close. So let me try other angles. So md equal to say 20. Okay, went to 20.08. That's very close. Let's do one more, or a few more actually. md equal to say 180. Yeah, it moved to 179.86. So let me set it back to 0 so you can see the pointer actually correlates to the angle. So md equal to 0. Yeah, and that's the 0 position. So let me do md equal to 90. Yeah, pretty accurate. That's 89.93. Obviously, the gearbox is not perfect, and floating point math is not always exact, but I'll say that's pretty close. Let's do one more. Say 360. md equal to 3. No, actually, I'll do 359. Yeah, that's very close to the 0 position at 358 degrees. So let me just do one more just for fun. I can honestly do this all day. It's just so much fun to watch the servo position itself. So let me just do one more. md equal to say 85. Yeah, and that's 85.06. Again, pretty close. One more thing I wanted to mention, the magnetic rotary encoder is a free spinning encoder and it does not have a home position. So when I power up the servo, it assumes the current position is the 0 position. So currently it can't ohm itself. So if I was to use this servo in a system or a similar design, I'll probably also include a limit switch so that the servo can ohm itself when you first power it up. So that's it for this video. I'll have all the original design files for this project on my GitHub repository, including the schematic and the Gerber files for the magnetic rotary encoder. You can of course buy the magnetic rotary encoder from my Tindy store, but if you prefer to manufacture and assemble the boards yourself, you can just download the Gerber files and then maybe send that off to GLC PCB to manufacture for you. You would of course have to source the components yourself. Thank you guys for watching. Please leave a thumbs up if you've enjoyed watching this video, and also consider subscribing to the channel if you like projects like this, and hopefully I'll see you in the next video. Bye.